Hello, this is the Unit 2 Module 1 Virtual Office Hour. We covered these questions in detail during the office hours this week, Tuesday, Wednesday, Thursday, and Friday. And so if you have any questions regarding calculations, potential energy, kinetic energy, things of that nature, then this video is designed to answer those particular questions. So we go through a calculation here where we're given the lambda in nanometers, and I've placed in every calculation this box here, which will contain the equations given on the previous exams that are under our exam content. Okay, so lambda must be in meters, right? So if you're going to do any calculations, please make sure lambda is in meters, because when we calculate the energy per photon, hc divided by lambda, we need to have lambda in meters. So when we put this calculation together, so the numerator are two constants given to us, and oftentimes, well, you'll be given the conversion factor, so 10 to the 9th nanometers is 1 meter. So 122 nanometers into meter to 4 meters, you divide it by 10 to the 9, and you get 1.22 times 10 to the minus 7 meters. When we do that, we see that the 1.22 times 10 to the minus 7 meters goes to the denominator, and we get 1.63 times 10 to the minus 18 joules per photon. Okay, so what if we wanted to calculate the frequency? What if we wanted to calculate energies per mole of photon? So we're going to do this several times in the video. So we'll do it with the first one. So here the frequency is given as c divided by lambda. Keep in mind that frequency is always given as the Greek letter nu, which looks like a fancy V. So 3 times 10 to the 8 meters per second divided by 1.22 times 10 to the minus 7 meters. We put that in, we see the frequency is 2.46 times 10 to the 15 reciprocal seconds, and this unit is 2.46 times 10 to the 15 hertz. The energy per mole of photons is you would take the energy per photon and multiply it by Avogadro's number. So 1.63 times 10 to the minus 18 joules per photon times Avogadro's number of 6.02 times 10 to the 23rd per mole. When we multiply that, we get exactly how much energy there is in a mole of photons, which is 980,865 joules per mole. We divide by 1,000 to get the kilojoules, and it's 981 kilojoules per mole of photons. So these are typically the types of calculations you have to do in Unit 2, Module 1. Let's do some more practice with that. So here we have 3 different wavelengths, and so we're going to convert them to meters and calculate the amount of energy in 1 mole. So it's really good to practice. So my suggestion is to try doing this and then compare with the work we're about to demonstrate. So at 100 nanometers, keep in mind these are going to be our conversion factors, 10 to the 9th nanometers for every 1 meter. Micron is 10 to the 6th micrometers for every 1 meter. And there are 10 to the 2 centimeters for every 1 meter. We convert the nanometers into meters, and we get 1 times 10 to the minus 7 meters. The amount of energy per mole of photons is the energy per photon times Avogadro's number, just like we did in the previous problem. We put this together. That's the numerator. H times C times Avogadro's number, divided by the wavelength, 1 times 10 to the minus 7 meters, and we get the amount of energy per mole of photons, which is about almost 1,000,000 joules. If we divide by 1,000 to get kilojoules, we see that we have 1,196 kilojoules per mole of photons. Lots of energy in ultraviolet light. Do the same thing for 10 to the 10 microns, which is infrared radiation. Divide that, to multiply that by 1 meter, divided by 10 to the 6th micrometers. We get 10 to the minus 5 meters for the wavelength. Put it into the formula. So that's h, c, and the Avogadro's number divided by the new wavelength we just obtained. We get the amount of energy in a mole of photons, which is which is about 11,966 joules per mole. We divide by 1,000 to get kilojoules, and it's 11.97 kilojoules per mole of photons. The microwave is at 1 centimeter. We say 10 centimeters. It's 1 centimeter. 1 times 10 to the minus 2 meters. So the energy in a mole of photons, put this in the formula. We have the same numerator, 3 times 10 to the 8, Avogadro's number, divided by the new wavelength of 1 times 10 to the minus 2 meters. That gives us an energy per mole of photons at 11.97 joules per mole of photons. Divide that by 1,000. Oops, should say 1,000 there. And it's 1.12 times 10 to the minus 2 kilojoules per mole of photons. So again, these are the types of calculations. Given any wavelength, you should be able to calculate the energy per photon and multiply it by Avogadro's number to get the amount of energy in a mole of photons. So we worked with this graph, or this image, in explaining absorption and emission. So here, keep in mind, absorption is shown as arrows pointing up. Emission is shown as arrows pointing down. So absorption, arrows are pointing up. That's because it absorbed a photon. The bigger the energy gap here, right? So the bigger the difference in energy levels, the higher the energy of the photon. So that's really important to keep in mind. It's also the higher the frequency and lower the wavelength. So these are really important aspects when you start comparing relative energies, as we'll see is done in the homework that we'll be working through in a little bit. Emission, arrows are pointing down. Photon emitted, and the higher the energy gap, right? So the higher the energy and frequency and the lower the wavelength, the larger the gap in the difference in energies. Okay, so that's really important. So red is going to have the lowest energy, lowest frequency, largest wavelength. Blue will have the highest energy, highest frequency, lowest wavelength. All right, and we talked about this question in class. So here we want to assign changes in potential energy and kinetic energy from absorption and for emission. So for absorption, the story is that we have an electron that's close to the nucleus. It absorbs a photon and goes to an outer orbit of the farther away from the nucleus. So the electron is farther away, so the potential energy must go up. If the electron is now going from a smaller orbit to a larger orbit, the speed is going to decrease and the kinetic energy goes down. So in absorption, potential energy goes up, kinetic energy goes down. In emission, we'll see there's the opposite process. So we start off with a very big orbit, electron far away from the nucleus. It then emits a photon. We now go to an inner orbit. So the electron is now closer to the nucleus. Potential energy must decrease. The electron now has gone from a larger orbit to a smaller orbit, and so the kinetic energy, so the speed decreases and the kinetic energy must increase. So the smaller orbit, speed increases, kinetic energy increases. Just keep in mind that in emission and absorption, potential energy and kinetic energy go in opposite directions. That would make selection C correct. In absorption, electrons start at low potential energy and end at high potential energy. They start at high kinetic energy and end at low kinetic energy. That would be a true statement. All right, so this particular problem was also worked out in class through an activity. And so here we have several statements about CO2, and then we want to investigate their validity. So first, the wavelength is given in microns, and so 1 meter is 10 to the 6 micrometers, and that converts into 10 to the minus 6 meters, because if we take 4.4 micrometers, use the conversion factor, 1 meter is 10 to the 6 micrometers, we get 4.4 times 10 to the minus 6 meters. So for a range of 4.1 micrometers to 4.4 micrometers, that would correspond to 4.4 times 10 to the minus 6 meters to 4.1 times 10 to the minus 6 meters. Next, are these the range of frequencies we'd expect for this wavelength? And so we take the speed of light, 3 times 10 to the 8 meters per second, divided by 4.4 times 10 to the minus 6 meters, and we get 6.8 times 10 to the 13 reciprocal seconds, and that's 6.8 times 10 to the 13 hertz. So yes, this is the range of frequencies we'd expect for these wavelengths. It's true, CO2 absorbs light at particular frequencies and not all frequencies. That's true because there are gaps in the spectrum. So at some absorbances, very particular frequencies, CO2 absorbs, then you move the frequency a little bit and then there's no absorption. That we can observe from the gaps in the spectrum. The CO2 absorption spectrum corresponds to the energy levels of the molecule. That's true. Infrared light comes in with a certain photon energy, hc divided by lambda, or h nu, and that has to exactly equal the energy difference between the energy levels of the CO2 molecule. So we're exciting that exact difference using the infrared light. Here we have the qualitative analysis of the wavelengths here, and so we want to rank energy. So keep in mind energy is proportional to 1 over lambda. That means that, let's keep in mind that the nanometer is smaller than the micrometer, which is smaller than the centimeter. So the centimeter is the largest wavelength, the nanometer is the centimeter is the largest wavelength, the nanometer is the smallest. That means the energy of the nanometer has to be the largest, the energy of the micrometer, and then the energy of the centimeter must be the lowest, right? So it's the lowest energy, highest wavelength or greatest wavelength. This has to be the highest energy because the nanometer is the lowest wavelength or the smallest wavelength. That means the energy of the microwave must be the lowest. It's the one at centimeters. Then the energy of the UV, which is in nanometers, must be the highest. And that would make answer B correct. All right, so here we have a absorption. Right, so this is the minimum energy. So we want to calculate, we have 4 absorption peaks. We want to know what is the minimum energy in kilojoules per mole to produce an electronic transition in this molecule. So what we're going to do is analyze each of the peaks. So peak A is 250 nanometers. Peak B is about 350 nanometers. Peak C is about 425 nanometers. And peak D about 650 nanometers. What we want to do is rank the wavelengths and energy. So 250 is definitely the lowest wavelength. So it's got to be the highest energy. 650 nanometers definitely has to be the highest wavelength we see, and then correspondingly would be the lowest energy. So peak D is the lowest energy necessary to excite this molecule. The energy per mole of photons is the energy per photon times Avogadro's number. We take 6.6 times 10 to the minus 34 times 3 times 10 to the 8 meters per second. Convert the wavelength into meters and multiply by Avogadro's number. If we do that, we get 3.06 times 10 to the minus 19 joules per photon times Avogadro's number, 6 times 10 to the 23 per mole, and we get 184,100 joules per mole. If we then convert this into kilojoules by dividing by 1,000, we would get 184 kilojoules per mole. Looking at the selection available, we would see that the top answer would be the correct answer. Next, we want to relate the transitions that we see in the absorption spectrum to the energy diagram. So absorption, remember the general characteristics for absorption is that the arrows are pointing up. So T1 and T3 are absorption peaks. T2 and T4 are emission peaks. So we would select for this problem T1 and T3 as the peaks as possible transitions in the spectrum given to us. All right, so this question comes from the homework. Several students have asked about it. So here we have an energy diagram on the left and a emission spectrum on the right. We have intensity on the y-axis showing the peaks, so high intensity are peaks, and we have on the x-axis the different lambdas where the transitions occur. And so we see that the lowest lambda, the lowest wavelength is peak 1, the highest lambda is peak 4. So the highest lambda corresponds to the lowest energy. The lowest lambda corresponds to the highest energy. When we look at the spectrum, we see that E is the highest energy emission signal. B is going to be the lowest energy emission signal because it has the smallest energy gap, and E has the highest energy gap. So that would make 4, peak signal number 4, at the highest wavelength, lowest energy, that would be B. At 1, which is the highest energy, lowest wavelength, that would be E. And then F would be the next highest, and then C would be the next one. So remember, the energy gaps are proportional to the energy. So B is the smallest energy, largest wavelength. E is the largest energy gap, lowest wavelength. This question is from the exam content page of Fall 16. So we're given that there are 3 different transitions. A 900 nanometer, which is the highest wavelength, lowest energy. 532 nanometers, which is the lowest wavelength, highest energy. So if we were ranking these from the energy spectrum, we would rank the transitions as E1 to be the greatest energy, E3 to be the next greatest, and E2 to be the smallest energy. That means, and we'd also assign that E1 is under absorption, E2 is showing emission, and E3 is showing E3 and E2 are both showing emission. Based on this energy ordering, we would put E1 at 532 nanometers. This would be the lowest wavelength, highest energy. E3 would be the intermediate, 566, and then the highest wavelength, lowest energy would be 900 nanometers. That would correspond to answer D. So it's really important to feel comfortable with the qualitative aspects of energy and wavelength and how they can help you assign spectra, transitions between the different energy levels. We also explored in the office hours calculations of one of these three wavelengths. So what we did was we would calculate the frequency, the energy per photon, and the energy per mole of photons in kilojoules per mole. So first we're going to use the equation that the speed of light is equal to the wavelength times the frequency. So if we know the speed of light, which we always do, and we divide it by the wavelength in meters, then we can get the frequency. And so by converting 566 nanometers to meters, it's 5.66 times 10 to the minus 7 meters. When we do this calculation, we get 5.3 times 10 to the 14 reciprocal seconds, which is 5.3 times 10 to the 14 hertz. So the frequency calculation always involves taking the speed of light, c, and dividing it by the wavelength. Keep in mind that nu is the frequency. If we want to calculate the energy per photon, we can take h and c, they're constants, divided by the wavelength, 5.66 times 10 to the minus 7 meters, and we get 3.5 times 10 to the minus 19 joules per photon. Want to know how much energy is in a mole of these photons? We take the energy per photon, multiply it by Avogadro's number. And if we do that, we get the energy per mole of photons is 211,423. If we divide by 1,000 in kilojoules, we get 211.4 kilojoules per mole. So make sure that given any wavelength, you can calculate frequency, you can calculate energy per photon, and you can calculate the energy in a mole of photons. All right, and the last question that was covered in office hours is predicting the change in kinetic energy and potential energy in transition 1. All right, so transition 1 is an absorption. It's going from low potential energy to high potential energy. So it's starting at low potential energy, ending at high potential energy. This is going to be true for all absorption. Keep in mind the nucleus is way down here at the bottom. And so these energy levels kind of look like this. And so this will help us picture the change in kinetic energy. So we're starting at an inner orbit in absorption, going to an outer orbit. The smaller orbit, the speed is higher, so the kinetic energy is higher, and we're going to a larger orbit where the speed is lower and the kinetic energy is lower. So given this information, we would pick A or D. The potential energy definitely has to increase as we're going through absorption. The kinetic energy cannot increase with the change in potential energy. It is that the kinetic energy decreases because of the bigger orbit. Okay, so that would be answer number D. All right, so this represents all of the questions that were covered in office hours, and I hope this helps you with the homework and as you prepare for the exam on Unit 2, Module 1.